have looked at refraction, but I want to do an example or two of this. So first I'll do this. I'm going to say we have an interface and I'm going to have air up here and glass down here. I'm going to give air an n of 1 and glass is actually a pretty loose term. There are all kinds of things that qualify as glass, so you'll see all kinds of different numbers here. 1.5 is a nice number, and that's one that we're going to use right now. Let's say I have a ray of light that's incident on here, and maybe I even have maybe I have an example that says I've got this line that's incident at an angle of 60 degrees with the interface. So or with the surface, if you like. But we know right away we don't want the angle with the surface. What we want is the angle with the normal. So let's draw in our normal. If that is 60 degrees with the surface, then that means I have 30 degrees. Theta incident equals 30 degrees. Now, one thing that I pointed out but didn't really spend a lot of time on in the other video, in the introduction video, is this. I said sometimes you get this reflected ray. Just looks like this. And here's my theta reflected. But I also have this transmitted ray. So anytime that I'm meeting a surface, I'm reflecting and I'm transmitting. If I've got a surface that's mirrored like this, then the implication is that I'm doing mostly reflection. But anytime I'm doing the one, I'm always doing the other, at least to some degree. I just might not be asked about both. So maybe I want to find the angle of the refracted ray. I am refracting off of this. This is what I would get if I didn't refract, if I was going from air to glass, or from air to air, or from glass to glass, and the medium were not changing. I would keep going in the path that I'm going. Instead, I'm going to a higher I'm going from an n equals 1 to a higher index of refraction, n equals 1.5, which means I am slowing down. If I'm slowing down, I'm going to bend toward the normal. So I expect my refracted ray to bend toward the normal. But now I'll do it. I'll do the problem. I'm going to say n incident sine of theta incident equals n transmission, or n refracted, times the sine of the refracted angle. That's what I'm looking for. So I'm going to solve. The sine of my refracted angle equals n incident sine theta incident over the second medium. I'm not looking for the sine of the angle, I'm looking for the angle itself. So what I would like to do is reverse sine this thing, inverse sine this thing. Or if you are a math person, arc sine this thing. Sine and inverse sine cancel each other, or they're inverse functions anyway, so theta t equals the arc sine of, that's what this is called, the arc sine of n incident sine theta incident over n t. So I'm going to get an inverse sine of 1 times the sine of 30 degrees all over 1.5. I'm going to be careful and make sure that my calculator is in degree mode. And I'm going to get 19.5 degrees for my refracted angle. There might, in this, also be a question of how do these questions get harder? Here's how I make this problem harder. I have a block of some kind of glass. We'll say it's a very light glass. Maybe make this an n equals 1.2, and here's n equals 1.0 out here. And I'm going to have a light ray that comes in, and we'll have it come in right around 45 degrees. We'll go theta incident equals 45.4 degrees. Meaning I'm measuring this angle right here. Here is my normal, and what happens, as I know, if I did not refract, I would keep going this way. I'm moving into an index of higher refraction, a higher index of refraction, so a lower speed, so I'm going to bend toward the normal. So I'm going to bend something like that. And there's my theta 2. I do know n1 sine theta 1 equals n2 sine of theta 2, so my theta 2 is going to be the inverse sine n1 sine theta 1 over n2, and I can plug in those values. 1.0 times the sine of 45.4 degrees, admittedly kind of a goofy number, over 1.2, and I come up with a theta 2 that is 36.4 degrees. That is going to be incident here. So I'm going to make a second normal. And I'm actually going to make a triangle out of these. This is a right triangle, so what I know, this angle is 36.4 degrees. This is a right triangle. They have to add up to 180, and there's a 90 degree angle. So this angle, theta 3, which is what I'm hoping for, because that's going to be what's incident onto my new normal, is 90 degrees minus 36.4 degrees, and that gives me 53.6 degrees. If I were to keep going unrefracted, I would go something like this. Yeah, something like this. But I'm moving into a higher speed area, or a lower index of refraction, which means I'm going to have to bend, this time away from the normal. So there is my theta 4. And I'm going to use the same equation again, except now I'm on 3 and 4. n3 sine theta 3 is n4 sine theta 4. Theta 4 is going to be the inverse sine of n3 sine theta 3 over n4. I can plug in some numbers. This is the inverse sine of 1.2 sine of 53.6 degrees all over 1.0, and I get that my theta 4 works out to be 75 degrees. So I'm doing a two-part refraction, and In the one, I'm bending toward the normal, in the other, I'm bending away from the normal, but in both of those cases, I'm kind of moving more toward a steeper down. It's just different because the normal becomes horizontal because I'm hitting this corner. That's it. That's refraction with a couple of examples.